So last time, we went through the process of doing control volume analysis, deriving expression for temperature. Right? We went through all these 7 steps, and then we got to the point of enforcing boundary conditions. In this example, we just assumed that generation is 0 and that it's steady state. So we only have heat flowing in and heat flowing out, and then we just do the differential analysis that way. We also did a problem and discussion on this. Today what we're going to do is talk about this concept called thermal resistance. All right, so thermal resistance is this idea that kind of helps us simplify the analysis so that we don't have to do that kind of complex analytical derivation every single time. So think about this example that I've got on the left here. This is just like the wall behind me, well, external, but maybe your apartment wall, whatever. You have drywall, then you have some insulation, then you have plywood, then you have some siding. And the idea is that we want to model heat flow from the interior of the house or whatever to the exterior. So if you're going to do this, and you're given the tools that we were left with last time, what would you do? Well, all these different materials have different properties, have different thicknesses, and so if you're trying to model this, basically you start off over here, and we're going to have a whole domain that's just related to the drywall. Then you solve the boundary conditions between the drywall and the air and the drywall and the other material, and you just keep going. So to do this, you'd have to solve 4 different analytically derived and boundary condition enforced equations to do that. And that's really tedious, right? It's kind of annoying to do that. So instead of doing that, we can use this idea of thermal resistance to just cut all of that out and kind of just run right to the solution. So this approach has limitations, right? There's only certain scenarios in which it's valid, but in those scenarios, it's a really useful tool. So not only is it useful for simplifying the analysis, but it's also a really good, like, back of the envelope type check for just understanding the problem. So, when we're teaching more complicated heat transfer problems, like particularly in the grad level class that we teach, we always focus on starting with a resistance network or a resistance model because it gives you that intuition of what's going to happen, and then you solve the more complicated problem and check it against the simple model. Okay, so thermal resistance, let me tell you what it actually is. So there's, I think you all have taken circuits, or hopefully have taken circuits. Have kind of an understanding of how voltage and current and resistance relate to each other. So thermal resistance is actually a lot like electrical resistance. I don't know, you all being mechanical engineers for the most part, maybe that doesn't help, but let's do the analogy and you'll kind of see what it means. So in a circuits analogy, and then a heat transfer analogy. Okay, so if you remember an electrical circuit, just a really simple example, you have, let's say, 2 nodes, and then you have some wire, let me just draw this a little better, some wire with a resistor. And let's say that we have a voltage over here that's relatively high, and we have a voltage over here that's relatively low, and we call this resistor R sub E. In this scenario, what's going to happen, right? High voltage, low voltage, you're going to have current flowing from left to right, right? So electrical current, like this. So we can call this I sub E, electrical current. Okay, so we can model this, and we can solve for the current I sub E by saying we're going to take the high voltage, V high, minus the low voltage, V low, and divide that by the electrical resistance R sub E. Hopefully this is all coming back to you now, right? Fine, so that's the circuit. You can have basically the same thing happening in a heat transfer application, right? Instead of voltage, though, now we have temperature. So our potential for heat transfer is temperature. So on the left, we'd have T hot. On the right, we have T cold. In the middle, we have some resistance, thermal resistance. We'll just call that R. And then you have heat transfer, Q dot. Okay, so in the same way that we model electrical resistance and with a lot of the same principles for stacking up resistances, looking at them in parallel, a lot of those same concepts apply to heat transfer, right? You have a potential, you have heat transfer, and you have some resistance to that or impedance to that. So we would compute Q dot in this case as Q dot is equal to TH minus TC over R. Okay, so you can kind of guess maybe where our analysis is going to focus. We have to figure out what R is and how to get to R. So I'm going to spend maybe a couple slides doing that. All right. So again, starting with Fourier's law, let's go through and let's solve the problem, this conduction problem that's specified down in the bottom. So we're going from TH, which is a known hot temperature, to TC over this domain 0 to thickness in terms of X. So let's solve this, and then we'll kind of see where the resistance idea comes up from that. By the way, I mean, hopefully at this point you kind of are becoming more familiar with the procedure to do this, so I'm going to kind of go through it quickly. Okay, so we have our heat transfer rate. If you do the control volume analysis, we're going to end up with dQ dot dx is equal to 0. Right? This is kind of borrowing from where we ended with our previous analysis. So let's take our rate equation, substitute that in. So d dx of minus k AC dt dx is equal to 0. Okay, so remember now we can cancel out for this problem, let's say constant conductivity, constant cross-sectional area. So we're just left with d squared t dx squared. Solve that by separation of variables as we did last time, and we have this equation, t equals c1 x plus c2. Okay, so speed ran that, but this is basically exactly the same thing that we did last time. Things to point out, right? T equals c1 x plus c2. That's a linear equation. Right? There's a linear equation there, and you can see that that's how it's plotted. So that's an important feature here, that it's a linear equation. And we'll see why later. Okay, so now we have this. Now let's take our general expression and enforce the boundary conditions. Then you'll see where the resistance comes in. So boundary condition 1. So the statement of the boundary condition, t at x equals 0 is equal to th. Right, that's just simply stating what is going to be enforced. To enforce that, we'll say th is equal to c1, so x equals 0, so c1 times 0 plus c2. So solve that, that gives us th is c2. Okay, easy enough. th. Boundary condition 2 is very similar. We're going to say t at x equals thickness is equal to tc. So then enforcing this, we say Tc is C1 thickness plus C2. So solve that, and that C1 is equal to Tc minus Th over thickness. All right, everybody see how we got there? It's just algebra. Okay. So we have our system of equations, our general expression, and then C1 and C2. So we're all set. We can actually write out the full expression for this. And it's temperature is equal to Tc minus Th over thickness times x plus Th. All right, so that's our solution for this problem. Okay, so that's fine. We have our specific solution. How does this help us with resistance? Remember, resistance that we just had for our resistance analogy is in terms of heat transfer. So looking up here, sorry, I'll keep that there. So looking up here, Q dot, this is a relationship between Q dot and temperature and resistance. So let's take our temperature equation, get it back in terms of heat transfer. So how do we do that? Well, we say, plug it into Fourier's law, right? So we're going to say Q dot is equal to minus K AC dt dx, so that's d dx of this whole thing, right? Tc minus th over thickness times x plus th. Okay, so if we do that, th goes away, we're left with just what's multiplying that x term. So Tc minus Th over thickness times minus K times AC. Okay, so that looks like, let's just write it out here. Q dot is equal to minus K AC over thickness Tc minus Th. Okay. Give you a chance to write that down. So what are we left with here? Again, remember, we're looking for Q dot is related to a temperature potential and some resistance. So we have our resistance, right? The resistance is just all that stuff that's multiplying the temperature potential. So for this problem, we can say R, this thing we're calling thermal resistance, is equal to, let's take the minus sign and bring it in. So we actually, let's do this. So I'm going to swap these around. You can do this in your notes too. H minus C. I'm just swapping it around with the minus sign. So the resistance for this is just thickness over K times AC. Right? This is our thermal resistance in a plane wall. So this will show up again and again, right? This is a formula that you use all the time, thickness over KAC. So if I know the thickness K and AC, then I can compute, just by knowing something about the temperatures, I can estimate my heat transfer. This, by the way, I mean, we've gone through this. This is the exact solution. So this works. It's an exact solution for this problem. If we start getting more complicated situations or the boundary conditions are different, then it no longer applies, right? This is only for the known temperature boundary conditions for a plane wall situation.